Hello and welcome to Circuit Shepherd. In this video, we'll investigate how to design inverting Schmitt-Trigger circuits with Circuit Shepherd. First, we'll demonstrate that the task of designing an inverting Schmitt-Trigger can in principle be transformed into a task of designing a non-inverting operational amplifier circuit. After that, we'll use Circuit Shepherd's capability of measuring discontinuities to provide a more direct way of designing Schmitt-Triggers. So let's start from the non-inverting operational amplifier circuit, which we already know. In this particular case, the DC transfer curve is defined by two DC sweep design targets. Additionally, we assume that our circuit has a single supply of 5 volts. To create the corresponding Schmitt-Trigger circuit, we make an entangled copy and isolate the net labels. Therefore, besides the entanglements, the new circuit is completely independent from the original. We also need to remove the redundant design targets. To transform the new circuit from an amplifier into a Schmitt-Trigger, we simply replace the operational amplifier with the comparator part, while also reversing the input polarities. For demonstration purposes, we just place bigger versions of the thumbnail plots, stacking them so that they exactly overlap. Now we can clearly see that the DC sweep design targets also define the switching points of the Schmitt-Trigger circuit. Note that this is fulfilled only if the particular target values exactly match the supply voltages of the comparator part. Therefore, to change the hysteresis of the Schmitt-Trigger, we must modify the sweep values only. Also note that the DC transfer curve always must cross the first median between the Schmitt-Trigger switching points. Other hysteresis are not possible for this particular circuit configuration. Okay, so while this is a perfectly fine method to design Schmitt-Trigger circuits, Circuit Shepherd also provides an alternative way by directly measuring the discontinuities of the hysteresis curve. Note that the disco symbol always measures the discontinuity which is closest to its target value, regardless if the goal checkbox is checked or not. We can use the disco symbols to measure the actual switching voltages or to directly define them as design targets. In the later case, we don't need the operation amplifier circuit anymore. For the finish, one last hint regarding to disco measurements. As already mentioned, regardless of the goal checkbox state, the target value is always evaluated as a starting point for the discontinuity search algorithm. This is also the case for the corresponding tolerance settings, so always take care to leave them in a, at least roughly meaningful state, even if they are hidden in the property pane. Alright, stay tuned for more in the next videos. Thanks for watching. See you later.